So this is the last of the videos on the development of calculus, and I just want to pull a few last things together and go back to Leibniz, talk just a little bit about some of his contributions again, and mention one more time how Leibniz and Newton were creating this calculus at the same time, and working in different places, pretty much working separately, coming at it from very different points of view. So, Leibniz came at it from more of a mathematical point of view, Newton more scientific, and Leibniz methods, techniques, the language, the looks of it are much more like what we use today. And even though there was that huge controversy and the Royal Academy or Royal Society decided in Newton's favor, for most of Europe, they followed Leibniz work. And Leibniz had the advantage of having two students working with him, the Bernoulli brothers, and you've heard about the Bernoullis in some of your calculus classes. So they carried on his tradition. Okay, well, let's look at Leibniz here for just a minute. Just a couple of things. And one is, and this is a really big deal, we mentioned the notation, that the functional notation f of x is from Leibniz. The long, skinny little curly Q for the integral is from Leibniz. Come on. And he used that because it's a long S to represent sum. So this notation, the integral of f of x dx, we can thank Leibniz for that. Now also the product rule, Leibniz came up with that in 1675. And he said that the derivative of the product of two functions, f times g, is the derivative of f times the function g plus the function f times the derivative of g. In the summer of 1676, we know that he came up with the quotient rule, and we know how he derived it. He said, let z equal the quotient y over x. And what I want to do is find the derivative of z. I want to find the derivative of that quotient. So let's rewrite this division problem as a multiplication problem. X times y equals, x times z equals y. Take the derivative of both sides. And we'll get the derivative of x times z equals the derivative of y. But he already knew how to find the derivative of a product. So this derivative was the derivative of x times z plus x times the derivative of z equals dy. Now remember, he's trying to solve for dz. So let's take this equation and solve it for dz. I've got x times dz equals dy minus dx times z. Divide both sides by x. So dz equals dy minus dx times z divided by x. Right? And on the right-hand side, I'm going to multiply that fraction by x over x, and I'll get dz equals, in the numerator, x times dy minus dx times z all over x squared. And there's your quotient rule. that the derivative of y over x is x times is a fraction, and it's x times the derivative of y minus y times the derivative of x. Oh, wait a minute. I forgot. I'm almost finished, because z, what is z? Z is y over x. So this is x times dy minus where is it? Y over x times dx over x squared divided by x. I left out, I didn't do this quite right. When I multiplied this by x, I've got x over x, x times dy minus x times z times dx. I left out the z right, the x right here. All right, equals over x squared equals x times dy minus, okay, but z is y over x. So I've got y over x times zx times the x. Now we go, here we go. And so that's equal to x times dy minus y times dx all over x squared. I can't leave it like that because I want to solve this for dz in terms of x and y. And that's what I had left out, where I've got to go back in and substitute what z is equal to and then simplify. There you go. So there's the quotient rule. So that 1675 is the product rule. Summer of 76 is the quotient rule. Interesting that in the fall of 76, fall of 1676, he comes up with the power rule, which says that the derivative of a times x to the nth power is a times n times x to the nth power. Interesting, that's the way he derived the formulas, not the order in which we teach them. This one we do before we do the product and the quotient rule. Okay. So just to finish up with the calculus, we've talked about the fundamental theorem of arithmetic, the fundamental theorem of calculus. What about the fundamental theorem of arithmetic, the fundamental theorem of algebra? What about the fundamental theorem of calculus? All right, so back to the fundamental theorem of calculus. The fundamental theorem of calculus deals with this function f of x, and the condition is that the function f is continuous on this interval from a to b. It doesn't have to be over the entire domain, but it has to be over this interval from a to b, including a and b. And here's my notation that this integral from a to b of f of x dx represents the area bounded on four sides. It's bounded by the curve, it's bounded by the x-axis, left and right, it's bounded by x equals a and x equals b. Now, how would we figure out what that area is? If I know the antiderivative of f of x, and I'm going to represent that with the capital F of x, and since capital F is the antiderivative of little f is the derivative of capital F. So the the integral from a to b of f of x dx is capital F of b minus capital F of a. Find the antiderivative, evaluated at b, evaluated at a. That's the fundamental theorem of calculus. This is the theorem that connects your calculus 1 and your calculus 2 classes. It connects differential calculus and integral calculus. That right there, that's the crux of it. That's the amazing part. Now, just a quick note about two women in mathematics, Maria Agnesi. Maria Agnesi was an Italian mathematician. lived from 1718 to 1799. And she wrote the book Instituzioni Analytica. And this is the first surviving mathematical work by a woman. Can't spell it. Surviving. And this book is a unified treatment of algebra and calculus. It helped people to understand what calculus was all about. Also working on algebra, she studied this curve yx squared equals a squared times a minus y. And she called it the Versiera curve, which means to turn in Italian. So Versiera is very close to the word for witch. And unfortunately, that's what got connected with her. And she is frequently known as the Witch of Agnesi for no reason whatsoever. There wasn't a witchy bone in her body. But the curve that she studied that turned on itself had, unfortunately, the word in Italian is for a turn is very close to the word witch. Okay, so Maria Agnesi is a very important woman in mathematics. Another one to mention at this time is Emily du Châtelet, who was French, lived from 1706 to 1749. She was a companion of Voltaire, and she began the translation of the Principia into math. Not into math, into French. She supplied the math. So it would not be easy to take that and just word for word, take each of those words, change them over to their French word. No, to be able to do that, you would need to understand the mathematics behind it. And she did. Okay. Now, unfortunately, you can see she didn't live to be very old. So she began the translation, somebody else finished it. All right. So we are ready to move on to module 18 on Euler.